Hey guys, my name is IBM, and today I'm trying to start series of AS physics. However, I will start with the particle physics. Do not forget to subscribe, download the videos. You can watch them at your convenience. You can share, like the videos, write a comment. I'm always willing to rectify anything that you really feel is not really clear. You can just write a comment. I'll try my level best to rectify it. Okay, so let's go and see the course outline for AS Physics. Okay, so this is particle physics. It is particle physics, although the name has really slightly changed for examinations from 2022. You may find it being called atoms, nuclei, and radiation, but it's still particle physics, or I think it would later on be called nuclear physics. Now, what is special about this topic? If you're just leaving IGCSE, or you have just sat O level, this is related to the last topic you started in, the second last topic you started in IGCSE or O level physics, which was nuclear physics. So the concepts are going to be the same, except that they will be slightly more advanced and more knowledge will be obtained from this topic. Many times my students love this topic because it's just a few basics and the questions are always the same and very, very, very easy. I think this should be lesson one, and I expect that we shall have at least three lessons and the topic will be done. But before we start this topic, I prefer to start it with course with the learning objectives that we expect to achieve at the end of this lesson. So some of the learning objectives would include the following. You should infer from the results of the alpha particle scattering experiment the existence and small size of the nucleus. We shall be able to describe a simple model for the nuclear atom to include the protons, neutrons, and orbital electrons. We shall be able to distinguish between nucleon number and proton number. We shall use the unified atomic mass unit as a unit for mass. That unit will be very important in A-level paper 4. Then we shall understand that isotopes are forms of the same element with different numbers of neutrons in their nuclei. We shall understand and use the notation AXAZ for the representation of nuclides. We shall understand that nucleon number and charge or proton number are conserved in nuclear processes. We shall also describe the composition, mass, and charge of alpha, beta, and gamma radiations. We shall understand that an antiparticle has the same mass but opposite charge to the corresponding particle, and that a positron is the antiparticle of an electron. So we shall see that a positron is like a positive electron. We should state that electron antineutrinos are produced during beta minus decay, and electron neutrinos are produced during beta positive decay. Understand that alpha particles have discrete energies, but the beta particles have a continuous range of energies because antineutrinos are emitted in beta decay. Of course, the neutrinos, they could be antineutrinos or just neutrinos, which are emitted in beta decay. We shall be able to represent alpha and beta decay by a radioactive decay equation of this nature, as you did in IGCSE. We shall understand that a quark, is a fundamental particle. Of course, the last part of particle physics will be fundamental particles. So we shall understand that a quark is a fundamental particle and that there are 6 flavors or types of quarks, which are up, down, strange, charm, top, and bottom. We shall recall and use the charge of each flavor of quark and understand that its representative antiquark has the opposite charge. We should be able to recall that protons and neutrons are not fundamental particles and describe protons and neutrons in terms of their quark composition. We shall understand that a hadron may be either a baryon consisting of 3 quarks or a meson consisting of 1 quark and 1 antiquark. We shall describe the changes to quark composition that take place during beta minus and beta plus decay. And finally, we shall be able to recall that electrons and neutrinos are fundamental particles called leptons. And by the way, the learning objectives alone give you everything you need to know or to understand from the unit that we are going to explore. Even by reading through the learning objectives alone, I can pass most of the questions in particle physics. Okay, so let us start with a simple introduction to particle physics, and we shall start with the models of atoms. Okay, so in IGCSE or in chemistry to be specific, you might have talked about matter in most of your classes, or in some of your classes, you might have talked about matter. There is no way I can talk about particle physics or atoms, nuclei, and radiation without knowing or referring to matter as a whole, because the atoms are believed to be making up matter or are believed to make up matter. So the idea that matter is composed of very small particles, which are called atoms, was first suggested by the ancient Greeks about 2000 years ago. So the Greek people suggest that atoms were the smallest particles that were making up matter. That was about 2000 years ago. And it was not until the mid-19th century that any ideas about what is inside the atom were proposed. So before the mid-19th century, people did not care about what really makes up an atom. People were comfortable to believe that atoms were the smallest particles that were making up matter, and whatever makes up atoms was not a subject of discussion. Of course, later on, several theories, or after the mid-19th century, people now started suggesting what should be making up matter. And the first person we shall discuss here is the English scientist in the name of J.J. Thomson. J.J. Thomson was the first scientist to suggest what should be or what makes up an atom. Rather than just thinking of the fact that atoms are the smallest particles that make up matter, J.J. Thomson was concerned about describing what he thought makes up the atom. Of course, later on, another scientist in the name of Rutherford came up to either test J.J. Thomson's model to verify if it can continue to be accepted or to be rejected, and his observations later on led to the rejection of J.J. Thomson's model. So what was J.J. Thomson's model? What did J.J. Thomson propose? What was J.J. Thomson's model of the atom? So J.J. Thomson suggested that an atom is made up of a neutral particle. An atom is actually a neutral particle which, according to J.J. Thomson, is made up of positive charges, which he called the plums. Positive charges, which he called the pudding, with the negatively charged particles, which we called the plums, and these were distributed all over the positively charged material. So, J.J. Thomson's model therefore came to be called the plum pudding or the plum pudding model. So, the first model of the atom that we can talk about is the plum pudding model or the plum pudding model, depending on how you pronounce it. And according to J.J. Thomson, he suggests that the atom consists of a positive material, which he called the pudding, with negative plums or negative particles or negative charges, which he called the plums. And these were distributed all over the material, which made the material to be a neutral particle. So, according to J.J. Thomson, he is here suggesting that an atom is a positively charged material with negatively charged plums or negatively charged particles which are distributed all over the material, which makes the material to be a neutral particle. That is according to the English scientist J.J. Thomson. So now questions came up whether to agree that an atom is a positively charged material with negatively charged electrons distributed all over it, making it neutral. Was it therefore to be accepted indefinitely? Scientists now came up and started testing this model. But of course, before testing this model, after J.J. Thomson suggesting that an atom is a positively charged material with negatively charged particles distributed all over it, experiments which were carried out later on were able to show that the mass of an electron, which were the negatively charged particles distributed all over the positively charged material, experiments later on showed that the mass was approximately 9.11 times 10 to the power of minus 31 kilograms. And of course, later on, experiments showed that the charge of the negatively charged particles was approximately negative 1.6 times 10 to the power of minus 16 coulombs. So 9.11 times 10 to the power of minus 31 kilograms was later on called the rest mass of the electron, and minus 1.6 times 10 to the power of minus 19 coulombs was later on called the elementary charge, as we shall see as we shall see later on. So this was the first model of the atom, which we are calling the plum pudding model. An atom is made up of a positively charged material, which we call the pudding, with negatively charged particles, which we call the plums, distributed throughout it, making the atom to be neutral in nature or a neutral particle in nature. So questions started rising. And today, we use the idea of the electron, which was, of course, suggested by J.J. Thomson earlier on, to explain all sorts of phenomena that includes electrostatics, current electricity, and electronics. Of course, in your concepts of current electricity, you must have defined current as the rate of flow of charge carriers. And we believe that these charge carriers are basically the electrons, even when we are sure that the electrons move in the opposite direction to the current. So phenomena of electrostatics, that is charges at rest, flow of current or current electricity and electronics now use the idea of electrons, which were first suggested by J.J. Thomson. But like I said, experiments had to test and verify J.J. Thomson's model to see if it would continue to be accepted or not. So this now led to new scientists getting concerned and making scientists develop interest in investigating or coming up with explanations uh, for explanations on what really they thought makes up the atom. So we are now saying we started with matter, where the ancient Greeks suggested that matter is made up of atoms. So we had stopped there 2,000 years ago. But around the mid-19th century now, scientists got interest in understanding what really makes up the atoms. And like I said, J.J. Thomson was the first person to make a suggestion. However, his model would not last for long after 1906 when Rutherford and his friends started carrying out investigations. So this model, the J.J. plum pudding model, was later on discarded Rutherford, after Rutherford's famous alpha particle scattering experiment. So in 1906, while experimenting with the passage of alpha particles through a thin mica sheet, Rutherford noticed that most of the alpha particles passed straight through a thin mica sheet. This suggested to him that there might be a large amount of empty space in the atom. And of course, by 1909, he had developed what we today call the nuclear model of the atom. So it means J.J. Thomson's model was not sufficient enough to explain why most of the alpha particles were just going straight through uh, the atom, most of them without even any deflection, or most of them with very little deflection. So in 1906, Rutherford notes that most of the alpha particles passed straight through a thin mica sheet, and this suggested to him that there might be large amount of empty space in the atom. And I'm saying that by 1909, he had developed what we today call the nuclear model of the atom. So, what was this alpha particle scattering experiment? So we have just mentioned that they directed alpha particles through a thin mica sheet, and their observations showed that most of them went straight through. Of course, this experiment was repeated in 1911 with Rutherford and his colleagues. This time they replaced the mica with gold. So in 1911, Rutherford and his colleagues carried out further series of experiments using a gold foil in place of the mica to see if they would make the same observations. So they replaced mica with a thin foil of gold and directed alpha particles through a thin foil of gold. The alpha particles, by the way, had already been established to be positively charged. However, their observations were similar to those that they observed with a thin mica sheet. So they now started arguing that perhaps J.J. Thomson's model was insufficient. So before we dig deep into J.J. Thomson's model, Rutherford's alpha particle scattering experiment, let's have just a picture of the apparatus used in this experiment. So in this apparatus, so this is a simplified apparatus which is used in the alpha particle scattering experiment. We need a thin foil, it could be gold or mica, and we need a source of alpha particles which is directed towards the thin foil of mica. And of course, we need a viewing lens, or we need a viewing lens the other side, which could be a traveling microscope, to observe where the alpha particles would hit on the screen. And They observed that most of the alpha particles were going straight through the thin gold foil, and just a few of them would be bounced, would be deflected through large angles greater than 90 degrees. However, this experiment was carried out in a vacuum. So Rutherford's scattering experiment were done in an evacuated container like this one here. We don't need to know the diagram for examination purposes. I just want to give you a picture of how this apparatus, a simplified apparatus that was used in the experiment. So the experiment was carried out in an evacuated container, and there is a reason for that. Later on, we shall see that alpha particles are highly ionizing, and by highly ionizing, we mean they can easily knock out electrons in air molecules. And of course, the process of knocking out electrons in air molecules means that the alpha particles would lose their energy. So, Rutherford alpha particle scattering experiment were done in an evacuated container. If there were air molecules in the container, the alpha particles would scatter off the air particles as well, and this would distort the results. The alpha particles may also be absorbed by 6 centimeters of air, causing what we call ionization. Of course, in the process of ionization, I say the alpha particles would give out their energy to the electrons in air molecules, and by losing their energy, they can't travel any further. So we say they are absorbed. So the experiment was carried out in a vacuum to avoid ionization because alpha particles were highly ionizing, as we shall see later on. So the experiment is carried out in a vacuum. The experiment was carried out or is carried out in a vacuum so as to prevent ionization or to prevent ionization from interfering with the expected results. Okay. So let's now explore more about the simple mode of the atom, which we are going to call the nuclear mode. Having disregarded J.J. Thomson's model, because the alpha particle scattering experiment made different observations, then the simple mode of the atom became accepted. Now, most of the alpha particles went straight through. That would be expected. And it would, by the way, it would be in line with J.J. Thomson's model if all the alpha particles went through. But one of the things which were not expected was when a few alpha particles were deflected through large angles greater than 90 degrees. That was not expected. Why do we expect that alpha particles could go straight through? Because if J.J. Thomson's model was correct and all alpha particles went straight through, then it is accepted because after all the electrons were lighter in mass, they could be easily knocked out of the atom by the heavier and very massive alpha particles. But then, why is it that some alpha particles were deflected through large angles? This was not expected. So this was not expected. And it means another model had to be developed. And I said by 1909, a new model which is called the Rutherford's the nuclear model was developed. And I said in 1911, Rutherford and his colleagues repeated the experiment with Mika and agreed that J.J. Thomson's model was not sufficient. Rutherford directed a beam of alpha particles, which are the nuclei of helium atoms, as we shall see, and hence positively charged at the gold foil to test the nuclear model and how particles and how the alpha particles scattered from the gold foil. And the observations were quite shocking. And I'm saying this led to what we call the simple mode or the nuclear mode of the atom. So after Rutherford had presented his findings, the nuclear mode of the atom gained rapid acceptance. Which findings did Rutherford present? We are going to see what findings he presented. But the nuclear model became widely accepted, especially by chemists. This was partly because it helped chemists to explain phenomena of chemical bonding, the way in which atoms bond to form molecules. Those are chemical reactions or chemical bonding. So chemists loved this model very much because it helped them to explain how atoms bond together to form molecules. Of course, after the Rutherford's model, later on protons were discovered to be positively charged, equal and opposed to the charge of the electron. Remember, the charge of the electron was mentioned to be a minus 1.6 times 10 to the power of minus 19 coulombs. Of course, different experiments were used to determine the charge of the electrode, not the same alpha particle scattering experiment. However, its mass was too small to account for the entire mass of the atom, not until the neutron was discovered as an uncharged particle with a similar mass to that of the proton. So, when the proton was discovered, its charge was found to be opposed to the charge of the electron, so the charge was found to be positive 1.6 times 10 to the power of minus 19 coulombs. Unfortunately, its mass was too small to account for the entire mass of the atom. Later on, we shall see that the mass of the atom is 1.67 times 10 to the power of minus 27 kilograms. And scientists argue that this mass was too small to account for the mass of the atom. So later on, as experiments continued, the neutron was discovered, whose mass was whose mass, I mean, which entirely had no charge, and it had a similar mass to that of the proton, almost the same mass as that of the proton. So at least the discovery of the mass of a neutron, a neutron, could account for the mass of the atom because several neutrons could add up with the protons to account for the total mass of the atom. So the discovery of the neutron also helped scientists to agree with the Rutherford's model of the atom. Experiments later on show that the diameter of the atom is approximately 10 to the power of minus 10 meters. That was the diameter of the atom, approximately. Especially experiments by Robert Brown in the famous Robert Brown's experiment or the Brownian experiment. The diameter of the atom was approximated to be approximately 10 to the power of minus 10 meters. That is the simple model. So what is this simple model? What is this nuclear model? So let's explore Rutherford's alpha particle scattering experiment in more detail. So according to J.J. Thomson, the atom was a neutral particle. The atom was a neutral particle with which was just a positively charged material with negatively charged particles distributed all over it. But when alpha particles were directed through a thin foil of gold nucleus, what Rutherford found out was different from J.J. Thomson's model. So the plum pudding model was very insufficient to explain the structure of the atom. After Rutherford's experiment of directing alpha particles straight into a thin gold foil, then Rutherford therefore suggested that an atom consists of a central massive positive nucleus, which contains of protons and neutrons. So in this animation here, a source of alpha particles is directed towards a thin gold foil as shown here. And of course, we have a screen, and observations are showing that most of the alpha particles are going straight through. Most of the alpha particles were just going straight through. And the implication was that the atom might be entirely empty space. So when the alpha particles are directed into or are directed through a thin gold foil, most of the alpha particles were able to go through simply because most of the atom is entirely empty space. And therefore, Rutherford suggests that an atom could be consisting of a central massive positive nucleus, which contains protons and neutrons, surrounded with negative electrons revolving around the nucleus, as we are going to describe later on. But then the question would be, why are we saying that most of the alpha particles were going straight through? Why do most of the alpha particles go straight through? Perhaps most of the atom is empty space. So in this animation here, when alpha particles are directed into a thin gold foil, we see that most of them are actually going to go straight through. Just a few alpha particles are going to be reflected back, or they are going to be deflected through large angles. And as demonstrated by this animation, most of them go straight through, others are deflected through smaller angles, less than 90, and most of them are, and just a few of them are deflected. A few of them are deflected through small angles. So you can see that out of almost 2000, most of the alpha particles go straight through or deflected through small angles. 1 in 2000 alpha particles are going to be deflected backwards, or they are back scattered. So this means an atom may not be described as J.J. Thomson had suggested. So Rutherford suggests that an atom consists of a central massive positive nucleus which contains protons and neutrons, surrounded with negative electrons revolving around the nucleus, as illustrated by that animation there. And according to Rutherford's model, therefore, an atom is going to be made up of a positively charged nucleus, a positively charged nucleus, which is consisting of protons and neutrons, and then with electrons revolving around the nucleus. And since most of the alpha particles are going straight through, why can't we believe that most of the atom is empty space? That, by the way, can still be possible if J.J. Thomson's model is correct. But then, why is it that 1 in 2000 alpha particles is deflected through angles greater than 90 degrees? Why is it that 1 in 2000 alpha particles could be deflected through large angles greater than 90 degrees? That is now a question for us to contemplate about. And why is it that there is some deflection for some electrons, for some alpha particles when they go through the thin gold foil? So there are two things to think about here. Maybe there is a positively charged material, a positively charged particle, which covers a very small area. This is now what Rutherford called the positively charged nucleus. And because it covers a very small area, most of the alpha particles were able to go through because they don't come close enough. They don't come close enough to the center. So it occupies a very, very, very small volume of the atom. That's why we agree by saying, or that's why we agree to say that most of the atom is entirely empty space. Most of the atom is entirely empty space. Then the atom is made up of a central massive positive nucleus, which contains protons and neutrons. These are surrounded with the negative electrons revolving around the nucleus, as we have illustrated this here. So the electrons are not stationary. According to Rutherford, these electrons are revolving. They are moving around the nucleus in certain orbits, which orbits were later on, described by Bohr's model, Neil Bohr's model, which model you'll explore in quantum physics. So in quantum physics, you'll explore Bohr's model and you'll explain the orbits in which the electrons revolve. But for now, we shall concentrate on Rutherford's model. So Rutherford's model, therefore, has evidence, which we are going to call the evidences or evidence of Rutherford's model. So from our observation, we have seen that when alpha particles from a source or radioactive source are directed into a thin gold foil, Most of the alpha particles went straight through and they were detected onto the screen. Most of the alpha particles went through. And why are they all, most of them going through? It's because most of the atom is going to be empty space. And I'm saying this would still be expected with J.J. Thomson's model. After all, electrons were lighter, they could easily be knocked out by very massive alpha particles. But then, how about the few alpha particles which were deflected through large angles greater than 90 degrees? And how about the alpha particles which are deflected through very small angles? So according to according to Rutherford, he gave his explanation that when an alpha particle comes very close to the center of the atom, it is going to be backscattered through large angles greater than 90 degrees. So this is its original path. It is very close to the nucleus, so it is deflected through a very large angle greater than 90 degrees. This is an angle which is greater than 90 degrees. When an atom is very far, when the alpha particle is not very close, when the alpha particle is not very close to the nucleus, it experiences a small deflection as shown by this diagram here. When the alpha particle is far away from the nucleus, it will just go straight through. And since most of them just go straight through, it means they are very far away from the nucleus. So it means the nucleus must be very, very, very small, that there's only a very small chance of an alpha particle coming close to the nucleus. So that's why Rutherford concluded by saying that most of the atom is entirely empty space. So in his explanation, if we consider the path, just three paths of alpha particles as demonstrated here, if particle 1 is very far from the center of the nucleus, particle 1 is clear of all the nuclei and passes straight through the gold atoms with no deflection as it is not close enough to the small positively charged nucleus. So the particles which go straight through are far away from the positively charged nucleus. If we look at particle 2 is slightly closer to the nucleus. Therefore, it experiences some deflection. Why is it experiencing some deflection? Alpha particles were already established to be helium nuclei which were positively charged. And when they come close to the nucleus, if they undergo deflection, it is only because they are being repelled by something which has the same charge as themselves. Therefore, we could agree that the nucleus had the same charge as the alpha particles. Therefore, the nucleus was positively charged. So since the nucleus is positive, as well as the alpha particles, like charges repel, that's why we have that small deflection. Then when we look at particle 3 approaches the gold nucleus so closely that it is violently repelled by it and rebounds, appearing to have had a head-on collision. So because particle 3 is in a straight line, is almost in line with the center of the nucleus, that is its original path. It is deflected through a large angle greater than 90 degrees. This is an angle which is greater than 90 degrees. That deflection, of course, could not be expected, could not be explained by J.J. Thomson's model. But Rutherford is explaining that this large deflection is because this particle is perfectly in line or head-on collision with the nucleus, and is just one in 2,000 particles which get an opportunity to come close to the nucleus or to the center of the atom, which means the atom covers the smallest volume of the nucleus covers the smallest volume of the atom. But remember, the nucleus is where the protons and neutrons are found. That means most of the mass of the atom must be concentrated at this point in a very small volume. So particle 3 is backscattered, that is deflected at angle greater than 90 degrees. It does not pass through since both have the same charge. So particle 3 is going to be repelled and it is going to be deflected through large angles or a large angle greater than 90 degrees. So what should we note from Rutherford's model? Therefore, a few things we need to note from Rutherford's model. Number one, Rutherford reasoned that the large deflection of the alpha particles must be due to a very small charged nucleus. So that large deflection of this alpha particle in position 3 is due to the very small charged nucleus. And we agree that the nucleus should be having the same charge as that of the alpha particle so that the deflection can also be explained by the repulsive force. So from his experiment, he calculated the diameter of the gold nucleus to be about 10 to the power of minus 14 meters. So the diameter of a nucleus is approximately 10 to the power of minus 14 meters. Experiments involved in obtaining the diameter of the nucleus are beyond our scope. And it has since been shown that very large deflection of the alpha particles due to electrostatic repulsion between the positive charge of the alpha particle and the positive charge of the nucleus. So the only way we explain the deflections or the deviation from the original paths is due to repulsion between the alpha particle, which is positively charged, and the positive charge of the nucleus. And we have already seen that the closer the path of the alpha particle gets to the nucleus, the greater will be the repulsion, as we have seen above here. As the alpha particle gets closer to the nucleus, then the repulsion also increases. If it is perfectly in line, then the repulsion is the deflection is through an angle greater than 90 degrees. Also, the alpha particle and the nucleus both experience equal but opposite repulsive electrostatic forces. So, because they have like charges, they are both basically going to repel. But by Newton's third law, they will repel each other with a force which is equal but opposite in magnitude. So, what conclusions can we arrive at from Rutherford's model of the atom? Conclusion. Whether this force has a much greater effect on the motion of the alpha particle than on the massive nucleus of gold. So the alpha particle will be deflected, it will move backwards, but because the nucleus is extremely massive, the force has more effect on the alpha particle than the nucleus. So the nucleus is extremely massive. What conclusions can we make? Conclusion number one, Rutherford's alpha scattering by thin metal foils is an experiment that provides evidence of the nuclear model of the atom. So there is evidence that the nuclear model should be accepted, which suggests that an atom is made up of a positively charged nucleus, of course, which contains protons and neutrons, with negatively charged electrons, which are not stationary but they are revolving around the nucleus. So the results of the alpha particle scattering experiment should not be forgotten. Number one, we have seen from the animations that most of the alpha particles went straight through. They went straight through a thin metal foil or a thin gold foil, some with little or no deflection at all. Most of the alpha particles went straight through with little or no deflection at all, some with little or no deflection at all. What conclusion can we make? Why are most of the alpha particles going through? The conclusion we can make is that most of the atom is entirely empty space. Most of the atom is entirely empty space. And I say this was expected by if J.J. Thomson's model was to be correct. However, the deflection part was not expected. Most of the alpha particles going through could be predicted by J.J. Thomson's model, but the deflection part was not expected, and the result too was even not expected at all. A few alpha particles were deflected through large angles greater than 90 degrees. This was not expected. What conclusion can we make from this result? If some alpha particles are deflected through large angles, just a few, these are actually 1 in 2000. 1 in 2000 alpha particles was deflected through large angles greater than 90 degrees. So if 1 in 2000 is deflected, it means 1999 particles went either straight through or with little deflection. So why are a few alpha particles deflected through large angles? Maybe it's because most of the mass of an atom is concentrated in a small positively charged nucleus. So the reason as to why a few alpha particles are deflected through large angles greater than 90 degrees, it's because most of the mass of an atom is concentrated in a small positively charged nucleus, that if one of the alpha particles come very close to that point where most of the mass is concentrated, it is going to experience a very large electrostatic force, so that it is deflected, it is backscattered, or it is deflected through a large angle. So those are the conclusions that we can obtain from Rutherford's alpha particle scattering experiment. Question: in Rutherford's experiment, alpha particles were deflected at a thin gold foil. A small fraction of the alpha particles were backscattered through 180 degrees. Describe and explain how the fraction backscattered changes if each of the following changes are separately made. Number one, they use a thick foil of gold. A thick foil is used. Of course, when we talk about thickness, it means we increase the number of atoms. If we have more atoms, it means we have more nuclei. And if we have more nuclei, it means there is a greater chance of an alpha particle coming close to a positively charged nucleus. So it means the fraction backscattered increases in that case, because there is a greater chance of an alpha particle approaching one of the nuclei in the thick foil. So the fraction backscattered increases, so we expect more alpha particles to be backscattered if the material is thick, because thickness means more atoms present. More atoms means more nuclei present. So we don't expect, if we have a thin material and a very thick material, here we expect fewer atoms, and here we expect more atoms present. So we expect more nuclei in a thicker material. So we expect more deflection through large angles in a thicker material. Then if we use faster alpha particle scatter alpha particles, of course faster means speed, and which also means momentum, and maybe kinetic energy. You can try this with the two like poles of a magnet. If you give them a high speed to move towards each other, the repulsion, they may even touch before they repel, because the kinetic energy is high enough to overcome the force of repulsion. So if we use faster alpha particles, then it means fewer alpha particles will be backscattered. The reason? Because they will have greater inertia. The alpha particles will have greater inertia, and therefore the inertia would tend to carry most of them forward, overcoming the repulsive force. Then if we use silver, a silver foil is used, and they have told us that silver has less positive charge than a gold nucleus. So if silver has less positive charge, it means there's a smaller repulsive force. So we expect more alpha particles to overcome the repulsion and just pass straight through. So those which are backscattered are going to be fewer. So that question summarizes the alpha particle scattering experiment. More alpha particles are backscattered because of a greater chance of close approach to a gold nucleus. That is, if we use a thick foil of gold. If you use fast alpha particles, fewer alpha particles are going to be backscattered, because their great inertia would tend to carry most of them forward, overcoming the repulsion. Then if we use silver, which has less positive charge, then we expect that fewer alpha particles are going to be backscattered, because the repulsive force would be less. The repulsive force is less strong, therefore fewer alpha particles are going to be backscattered. Most of them will, fewer alpha particles are going to be backscattered because the repulsive force would be less, so most of them will just pass straight through. We need to point out a few things from the alpha particle scattering experiment. Few things to note here. Protons and neutrons make up the nucleus of the atom. So the nucleus is made up of protons and neutrons. Number two, the electrons that we have mentioned earlier on revolve around the nucleus in a cloud. Some electrons are closer to the nucleus and some are farther from the center of the nucleus. So they revolve around the nucleus in what Neil Bohr called allowed orbits or stationary states that you will mention in quantum physics. It is also important to note that the diagram that we mentioned above of the nuclear model was just a model of the atom. It conveys an impression of what an atom is like, but is not a completely true representation of the atom. So the model we drew in when we were starting the nuclear model, which consisted of a positively charged nucleus, which had protons and neutrons at the center or in the nucleus, with negatively charged electrons revolving around. This is not the actual model of the atom, but it's just a representation of the atom, which conveys an impression of what an atom is like. But this is not completely a representation of a true representation of an atom, because the electrons themselves revolve around the nucleus in a cloud. Some of them are closer and some of them are farther away from the center. So that is a very important point to note here. Of course, I know you use the same representation in chemistry, but that is just a representation. It is not the actual, it's not really what an atom really looks like. It is just a representation, you know. Okay, so we need to know a few more things. Number one, the masses and charge of each particle can be given below. We have been talking about these masses. The mass of a proton is approximately 1.66 times 10 to the power of minus 27. In some books, this will be quoted as 1.67 times 10 to the power of minus 27. The mass of the neutron is also 1.66 times 10 to the power of minus 27. In some books, it will be quoted as 1.67 times 10 to the power of minus 27. Of course, we have already mentioned the mass of the electron as 9.110 times 10 to the power of minus 31 in kilograms. I've talked about the charge of an electron as being 1.6. Of course, this is negative 1.602 times 10 to the power of minus 19, and the mass of a proton is the opposite, 1.6 times 10 to the power of minus 19. Of course, the charge of a neutron was established to be 0 because the neutron could not account for the total charge of the nucleus. So we should be aware of these masses. Although the mass of the proton and the mass of the neutron, mass of the electrons, are always quoted in the list of constants, we should be aware of the charges, even though the charges are always quoted in the list of constants. So it is impossible to simplify the above information by looking for patterns. I mean, it is possible to simplify the above information by looking for patterns. Let's look at the patterns in the information of the table that I've just drawn. First, notice that the electron and the proton have equal and opposite charges. A new unit of charge called the elementary charge, which is 1.602 times 10 to the power of minus 19 coulombs, allows us to assign values of positive E and negative E to the charge of the particle. So, because the proton was 1.602 times 10 to the power of minus 26, and this was positive, this is a proton. And an electron was negative 1.602 times 10 to the power of minus 27 kilograms. So by looking at the pattern, then we can assign the proton positive E and the electron negative E. So E is standing for the elementary charge. So that would be a new unit of charge, which we are going to call the elementary charge. Also, number 2, let's look at the pattern in the masses. Secondly, as the mass of the proton, neutron, and electron are very small, a more convenient unit is the atomic mass unit. We shall define the atomic mass unit in more details in paper 4 under a unit called nuclear physics. So, the atomic mass unit U is given as 1.66 times 10 to the power of minus 27 kilograms. This constant is also quoted in the list of constants in the question paper. So using this unit, this new unit, we can approximate the masses of a proton, neutron, and electron to be 1U, 1U, and 0.0005U. Because remember, the mass of the proton was 1.660 times 10 to the power of minus 27, or 1.67. And the mass of the neutron was also the same, but the mass of the electron was 9.11 times 10 to the power of minus 31 kilograms. So when you divide, this divide by that gives us 1 for the proton, 1 for the electron and neutron. Then for the electron, it would be 9.11 times 10 to the power of minus 31 divided by 1.66 times 10 to the power of minus 27, which gives us 0.0005 in unified atomic mass units. So the mass of the electron can be approximated to be as 0.0005 U. And by the way, this is the same as 1 over 1840 U. You might have mentioned this in chemistry as the mass of an electron. So this can therefore be summarized as shown here. In summary, a proton would be denoted as P11, an electron will be denoted as E0 minus 1. Later on, we shall also denote an electron as B beta as 0 negative 1. That is after we have talked about beta particles. Then the neutron, because it has no charge, the neutron will be denoted as N10. Then the charges, the proton is positive E because E stands for 1.6 times 10 to the power of minus 19 coulombs. And the electron is negative E, the neutron has no charge, or you can put there a 0. Then the relative masses in unified atomic mass units. This is having a mass of 1 U. This is 1 over 1840 U. And this is also 1 U. So that is the relative mass. That is the relative mass. Remember, this one is the same as 0.0005 U. So you can quote 0.0005 U. So that is the summary from looking at the patterns of those particles. So, having looked at the pattern of those particles, having explored Rutherford's scattering experiment, then what is the scale of things? So we can give a summary of the scale of things. How do we know things now, today? So it is useful to have an idea of approximate sizes of typical particles now. We have mentioned diameter of an atom, radius, or diameter of a nucleus, and so on and so forth. So the radius of a proton is approximately the same as the radius of a neutron, which is approximately 10 to the power of minus 15 meters. Now, when I talk about radius, it is equivalent to talking about diameter because diameter is just radius divided by 2. So the power of 10 for the diameter and the radius is approximately the same. So I could still say diameter or radius. Then the radius of a nucleus, of course, a nucleus is relatively bigger, but of course the simplest nucleus could be that of hydrogen. So the radius or diameter of a nucleus is approximately 10 power minus 15, 10 power minus 14, in that range. Then if it is an atom, the diameter or radius, the diameter or radius of an atom is approximately 10 to the power of minus 10 meters. These are quantities you should know, especially these ones here. You should have them at your fingertips. And lastly, the size of a molecule. I think a molecule could be bigger. It could be between 10 to the power of minus 10 meters to 10 to the power of minus 6 meters. A molecule can have a single atom or it can have several atoms. That's why the size could be relatively bigger than that of an atom or very close to that of an atom. So that is the scale of things. That is how we know some of these things at particle level, their diameters. And I'm saying a wise student should have these at their fingertips because they are very important. They help you to, they give you a picture of how small these quantities are at nuclear level. How these values are determined may not be a part of this syllabus. That is the scale of things. Okay, then let's also look at describing or description of atoms. Describing atoms. How would we describe and represent atoms? In one of the learning objectives, we saw that we shall be able to describe atoms or represent atoms using atomic notations such as X, A, Z, where A, of course, stands for, I think, nuclear number, and Z stands for atomic number. So to describe the number of particles in a given atom, we use this simpler notation that you use in chemistry. So to describe the number of particles in a given atom, we normally use that notation, and you'll always find that notation in chemistry, as it is even in nuclear physics and in particle physics. So we know that A stands for the nuclear number, where in chemistry I think you call it mass number. And Z stands for the proton number, where in chemistry I think you call it atomic number, commonly atomic number. For example, if you look at helium, helium, by the way, an alpha particle is going to be a helium nucleus, as we shall see later on. So if you look at helium, He4, this is 42. He42, not 4Z. So if you look at helium, for example, helium has 4 nucleons. The nuclear number is 4. And it has 2 protons, or the proton number is 2. So that notation is very common in chemistry. And the nuclear number is the sum of the number of neutrons and the number of protons. And then the proton number is what you call the number of, or is what you call, the proton number is what you normally call, the proton number is what you normally call the atomic number in chemistry. That's what we call the proton number. So we know that the nuclear number is equal to the proton number plus the neutron number. That is, the nuclear number is number of protons plus number of neutrons. The number of protons is the atomic number, and the number of neutrons is going to be the nuclear number minus the proton number. So if helium is 42 and I want the number of neutrons, I will get 4 minus 2. I think that is basic. You normally do that in chemistry. You normally do that in chemistry, so that is something very easy. So the sum of neutrons, the sum of protons and neutrons in the nucleus is what we call the nuclear number. Z is the proton number, and A is the nuclear number. The values of letters A and Z will always give you a clue of the name of the element. For example, helium, He42, we know that is helium, or an atom of helium, or later on we shall see that is a nucleus of it is an alpha particle, is a helium nucleus. And we have seen that the difference between A and Z is going to be the neutron number. In other words, my students normally prefer to write capital N for neutron number is equal to nuclear number minus proton number. This is the number of neutrons, not nucleons. Nucleons, that is A. Number of nucleons, that is A. And number of neutrons, my students normally use capital N for number of neutrons. So how would we therefore describe an atom? Let's see an example. So we are going to see an example of describing an atom. Describe the atom, the atomic structure of the following. I'll just describe one. So we have oxygen, we have lithium 73, we have uranium 23592, we have helium 42. Note, although the nuclide notation Az is commonly used, also be prepared to see nuclides using the form neon 20, neon 22. So some nuclides will be described like that, neon, or will be denoted like that, neon 20, carbon 12, carbon 12. So what is this 12? Neon 20. What is this 20? Neon 22. What is this 22? So here, what is given what is given here is actually the nucleon number is what is given, not the proton number. When we say neon 20, 20 is the nucleon number, not the proton number. When we say carbon 12, 12 is the nucleon number, not the proton number. So sometimes you'll see a nuclide described like this, especially in exams. So let's describe. I'm going to describe one of the atomic structures of the following. I need some space. So I am describing oxygen 16. I will use this space. Let me change the color. Which color should I use? Should I use green? So I'm going to describe oxygen 1688. So first of all, I note it is having 8 protons. Then 8 protons. Remember, protons are in the nucleus. So I have 16 minus 8. It also has 8 neutrons. Neutrons are also in the nucleus. So the neutron number is 8. The proton number is of course, proton number is Z. Proton number is 8. Neutron number is 8. These ones reside in the nucleus. And if the atom is neutral, the number of protons is the same as the number of electrons. So I expect there to be 8 electrons. And 8 electrons, these ones will revolve around the nucleus. We know that the approximate diameter or radius of an atom is approximately 10 to the power of minus 10 meters. That is the approximate diameter. If the number of electrons is the same as the number of protons, then total charge is going to be 0. So by stating all that, I have described this atom. So I'll say it has 8 protons and 8 neutrons. These ones reside in the nucleus. That's number one. 8 protons and 8 neutrons in the nucleus. Because it has 8 protons, I'll also say it has 8 electrons around. So I'll say 8 electrons orbiting around the nucleus. 8 electrons orbiting around the nucleus. That's number one. Because I've mentioned 8 protons and 8 electrons, I have the right to say that total charge is 0. Total charge of the atom is 0. Total charge of the atom is going to be 0. And of course, I know that the diameter of an atom is approximately, so I'll say diameter stroke radius of the atom is approximately 10 to the power of 10 meters. I've mentioned that in the scale of things. I can also say the atom is mostly empty space. The atom is mostly empty space, as predicted by Rutherford's mode. The atom is mostly empty space. So by stating all these, I have described the structure of the atom in details. I'll try the same thing with uranium. So the only thing which is going to change is this one here. The rest are going to be the same. So if it is uranium, if I'm describing uranium, I will only change the number of protons and number of electrons and number of neutrons. So if it is uranium, I will simply say it has, uranium is 238, it has 92 for protons. Then neutrons, I think it is 143 for neutrons. 143 for neutrons. Electrons will be 92. So I'll say uranium, it has 92 protons, it has 143 neutrons, it has 92 electrons orbiting around the nucleus. 92 protons and 143 neutrons in the nucleus. 92 electrons orbiting the nucleus. Total charge is going to be 0. Diameter is approximately 10 to the power of minus 10 meters for the atom. The atom is mostly empty space. I have described the structure of uranium in details. So these other three apply to all atoms. These ones will apply to all atoms. What will change is the first one only. So you can try that with the rest of the nuclei, with the rest of the atoms. So that is how we describe the structure of an atom. Okay, another example maybe. State the charge of each of the following in terms of the elementary charge E. Of course, I think we have already seen this. Proton, I think proton is simply positive E. So this is positive E. A neutron, this is of course 0. Nucleus, a nucleus is made up of several protons. It is the protons which determine the charge of the nucleus. So and the protons are positively charged. So it is positive Z times E. So this will be positive Z times E, where Z equals to the number of protons. So it will be Z, positive Z times E. Then a molecule, of course, a molecule has no charge. Then alpha particle, an alpha particle is a helium nucleus that we shall see later on. An alpha particle is going to be He42. It has 2 protons, so the charge is going to be positive 2 because there are 2 protons, but each proton has charge E. Then lithium. Lithium nucleus is 73. So that charge is going to be positive 3 times E because it has 3 protons. Sorry, this is a lithium nucleus. Then a lithium atom has a charge of 0 because it will have 3 protons plus 3 electrons. So total charge is going to be 0 for a lithium atom. So the atom will have a charge of 0, but the nucleus will have a charge of positive 3e. So that is that example, I think. Maybe let's also talk about the nuclear density of a particle, the nuclear density of an atom, or the nuclear density of a particle. When I talk about nuclear density, I'm referring to the density of the nucleus. Remember, we have seen that most of the mass is concentrated at the center of the atom. Most of the mass is concentrated in a very small positively charged nucleus. So it means we can assume that most of the density of the atom is at the center of the nucleus. So if we consider a proton as a small positively charged sphere, the moment we know its mass and radius, we can calculate its density. Remember, most of the mass is concentrated at the center of the nucleus. So if we know its mass and we know its radius, then we can calculate its density. For example, I'll just give an example. We know the mass of a proton. The mass of a proton is approximately, I think it's about 1.66 or 1.67 times 10 to the power of minus 27 kilograms. And We know the radius of a proton from the scale of things that we have discussed to be approximately 10 to the power of minus 15 meters. So I'll just choose a number, say 0.8 times 10 to the power of minus 15 meters. The power of 10 is the most important one. That is an approximation. So if I want to find the volume of a proton, remember I'm dealing with a proton, we can assume that the proton is spherical, and therefore its volume is the volume of a sphere, which will be 4 over 3 pi r cubed. So if I try to substitute, it will be 4 divided by 3 pi times the radius, which is 0.8 times 10 to the power of minus 15, and this is going to be cubed. So when I press the calculator here, so from my calculator, the volume of a proton is approximately 2.14 times 10 to the power of minus 45 meters cubed. That is volume. If I want to estimate the density of the proton, so density of the proton is going to be approximately equal to, of course, density is mass over volume. So this is going to be the mass of a proton, which is approximately 1.67 or 1.66 times 10 to the power of minus 27. Normally in the exam, the mass is quoted as 1.67 rather than 1.66. Divide by 2.14 times 10 to the power of minus 45. So I'll just press my calculator. So the density of a proton is 7.8 times 10 to the power of 17 kilograms per meters cubed. So we notice that this is approximately, this is roughly, it is almost 10 to the power of 18 kilograms per meters cubed. So this is extremely dense. So the proton has a density of roughly 10 to the power of 18 meters cubed when I just round off this, because this is 7.8, which is very close to 10. So it is approximately 10 to the power of 18 kilograms per meters cubed. So that's why we are saying the nucleus is extremely dense. Most of the mass is concentrated in the nucleus of the atom, because the proton is extremely dense, as shown by this calculation here. From the estimates, mass of the proton, the approximate radius of the proton, we find that the density of the proton is almost or roughly 10 to the power of 18 kilograms per meters cubed. So it means the atom's density may be mostly concentrated at the center or at the nucleus where the protons are found. So if we consider a proton as a small positively charged sphere, and we know its mass and its radius, then we can be able to estimate its density as shown here. But if we know the mass of the particle and we know its radius, if we assume that if we always assume that there's always little empty space between the atoms, then we can also estimate the volume of its atom. We can also estimate the density of the atom, and so on and so forth. For example, I think I need to give a very different example here. So I may need this space here. Let's say a live example before we go off this lesson. Gold has a density of 19,700. kilograms per meters cubed, that is the density of gold. And 193 grams of gold contains 6.02 times 10 to the power of 23 atoms. Use this information to estimate the volume of a gold atom and hence its radius. So we want to estimate the volume of a gold atom and hence its radius. I want you to always put it in mind that the mass of an atom is going to be approximately the same as the mass of its nucleus. Reason? Most of the mass of an atom is concentrated in the nucleus. The mass of an atom is going to be approximately the same as the mass of its nucleus. Reason being, most of the mass of an atom is concentrated in the nucleus because most of the atom is entirely empty space. It's the nucleus where we find most of the dense particles. Okay, so this information to estimate. Use this information to estimate the mass, the volume of a gold atom. Okay, let's try to estimate the volume of a gold atom. So this is density. This is mass of 6.02 times 10 to the power of 23 atoms. So I'm going to find the mass of one atom. Then I find the volume and hence its radius. I think I need to get another space. State any assumption you make. So the assumption I'm going to make is that I'm going to assume little empty space between different atoms. That is the assumption I'm going to make. So the mass, the density is given as 19,700 kilograms per meters cubed, and the mass of gold, which contains 6.02 times 10 to the power of 23 atoms, was 193. So the mass of one atom is going to be 193, of course, times 10 to the power of minus 3 kilograms, divided by 6.02 times 10 to the power of 23. Remember, 6.02 times 10 to the power of 23, if you're a chemistry student, that is called Avogadro's constant that we shall mention in nuclear physics. Use this information to estimate, we're going to use this information to estimate the volume. So we have the mass of one atom, we have the density, and we know that volume is equal to, because density is mass over volume, so volume is mass divided by the density. So this is going to be 193 times 10 to the power of minus 3 divided by 6.02 times 10 to the power of 23. Then we divide this by the density, which is 19,700. So I'll just check my calculator. 193 exponent minus 3 divided by 19700 times 6.02 exponent 23. So this is giving me the volume of one atom to be approximately 1.63 times 10 to the power of minus 29 kilograms. Meters cubed. That is the volume. Hence, find the radius. They told us to find the radius of the atom. Hence, the radius of the atom. So this is the volume of the atom approximately. Let's find the radius approximately. So we assume that the atom is spherical. So the volume of a sphere is 4 over 3 pi r cubed. So it means the radius is going to be equal to the cube root of 3 times the volume, 1.63 times 10 to the power of minus 19. Then we divide this by 4 pi to get the radius. So I have 3 times 1.63 exponent minus, so this is 29 minus 29 divided by 4 pi. then cube root. So this is giving me 1.57. Let me check this again. Three times 1.63 exponent minus 29 divided by 4 pi, then cube root of the answer. So this is giving me the radius as 1.57 times 10 to the power of minus 10 meters. Because this is just, most of these quantities are just estimates, I'll round off this to approximately 2 times 10 to the power of minus 10 meters. It is because it is an estimate. Estimates are good enough to a very small number of significant figures. So approximately 2 is a good estimate. So 2 times 10 to the power of minus 10 meters. So we also mentioned from the scale of things that the radius or the diameter was of the order 10 to the power of minus 10 meters. So it makes sense when I get 10 to the power of minus 10 meters as the radius. 10 to the power of minus 10 meters as the radius of the atom. So every time you calculate the radius or diameter of the atom, the order of the radius or diameter will be approximately 10 to the power of minus 10 meters. Okay, I think lesson 1 should end here. So I have assumed a little space between atoms. That's why I've come up with such a thing. So